Welcome to video 15 on the TTB course. This video is from part 4 of the course. In part 4 we consider techniques for monitoring TT systems. In this video we consider ways in which we can perform BISTs, that is built-in self-tests, while the system is operating. The material in this video is based on Chapter 15 in the ERES2 book. As usual, I suggest that if you've not yet read Chapter 15, you stop the video now, read the chapter, and come back and watch the video after you've read the book chapter. So let's assume that we've passed the low-level posts, as we discussed in video 13, confirmed that we're using the correct processor software, as we discussed in video 14, and confirmed that the processor software has not been corrupted, as we also discussed in video 14. Then we're ready to start our processor. Assuming that all processors pass such tests, our complete platform will be ready to start. From this point on, we will usually need to perform periodic built-in self-tests on each processor while the platform operates. As an example, let's consider an industrial control system that might be developed in compliance with IEC 61508. This will typically have a proof test interval of 20 years. The PTI represents the time after which the unit must be either subject to a complete test and verification process to ensure that it is in as new condition, or replaced. In most situations, the purchaser of the equipment will assume that the equipment can be used for the PTI and it will then be disposed of. There may well be no maintenance requirements or customer checks required or expected during the PTI. The unit must, in these circumstances, be able to monitor its own condition throughout the PTI and determine whether it is able to operate safely. If it cannot operate safely, it must enter an appropriate fail-safe state. So this means that we may have a SIL3 piece of equipment that's performing self-tests over a 20-year period, and that there is no other maintenance performed on the system. Ensuring that your system can operate safely over such an extended period is a non-trivial process. Let's consider another example, an automotive design developed in compliance with ISO 26262. In current automotive designs, it may be reasonable to assume that no car will be driven for more than 12 hours before it is restarted, and we might hope that nobody drives for as long as 12 hours. Anyway, this may reduce the complexity of some of the built-in self-test requirements compared with IEC 61508 at the present time. As ADAS and in due course fully autonomous vehicles become more common, it seems likely that some vehicles will need to be able to operate for much longer periods between restarts. Again, these may end up with operational periods that are probably not quite as long as some of those seen in industrial systems, but are likely to run for several days at least. So how can we perform appropriate built-in self-tests to ensure that our system is operating correctly? Let's start with the simplest solution. A simple but effective way of performing BISTs is to perform periodic same-mode resets. We discussed same-mode resets in video 8. If we perform a same-mode reset in a system that has a full suite of power-on self-tests, we can repeat all of the power-on self-tests from video 13 on a periodic basis. A list of the tests that we might perform is summarized below. In many systems, we won't perform such a set of periodic built-in self-tests. Instead, we'll integrate same-mode resets and segmented memory tests. If we simply perform a same-mode reset, this can be a simple means and an effective means of ensuring that the system can operate safely for long periods of time. However, it's not practical in all platforms, not least because of the time taken to perform the memory tests. When a system is first powered up, it may be acceptable to spend 500 milliseconds or more performing various power-on self-tests. While the system is running, we may need to complete a particular built-in self-test in around a millisecond in order to meet response time requirements. One consequence of these kinds of time constraints is that power-on self-tests will usually test the whole area of RAM and flash. Built-in self-tests will usually test only a small memory area at a time. To support such segmented tests, we need to keep track of the next block of memory to be checked, use some form of multi-stage task. If the system is going to be reset frequently, then we may need to store the current test status in a register variable so that the information about the next memory area to be checked is available after each reset. Note that the use of segmented memory tests is common even where we don't perform periodic same-mode resets. In practice, the situation is slightly more complicated. In practice, different RAM tests are usually used during power-on self-tests and during built-in self-tests. During posts, we usually perform a marching test on memory, as we discussed in video 13. During BISTs, we usually perform a GALPAT type test, a galloping pattern test. GALPAT tests have a higher diagnostic coverage for hardware than marching algorithms. However, they also have a higher computational load, and they usually need to be carried out in a segmented manner, as we discussed in a previous slide. To integrate same-mode resets and segmented memory tests, we might do so as follows. We'll perform all of the tests listed in the slide included here after a power-on reset. So we'll perform all of the tests listed here after the power-on reset. We will also perform periodic same-mode resets. These will again involve the tests listed here. With the exception of test 2 and test 3, these will be replaced by a series of segmented memory tests. So we'll only test part of the memory each time we check it in our built-in self-test framework. Note that we may decide that if we perform periodic same-mode resets, we may not check everything in this list in every built-in self-test. We may check some of the items in some tests and different items in different tests, but the principle is the same. So we're going to combine a cut-down version of our power-on self-test test suite with segmented memory tests. We need to consider a couple of important terms here. The process safety time, which is a term that comes from IEC 61508, and the fault-tolerant time interval that comes from ISO 26262 are two key terms. They both mean the same thing. They both refer to the interval between the occurrence of an abnormal platform state and the occurrence of an uncontrolled platform failure. So the PST or FTTI describe a situation in which no monitoring systems have been implemented and the abnormal platform state is therefore not detected by the platform. In many cases, the PST FTTI is measured in milliseconds. So if we take these two terms from IEC 61508 and ISO 26262, this is what they might look like. We have an abnormal platform state. After the process safety time, or FTTI, we end up with an uncontrolled platform failure. Clearly, we wish to avoid this. So we perform our BISTs and other monitoring in order to ensure that, for example, we can enter a fail-safe platform state before we would otherwise enter an uncontrolled or experience an uncontrolled platform failure. This is the purpose of our BISTs and other monitoring in the system. Of course, it may be possible to perform other forms of recovery. For example, a same mode reset might allow us to recover, etc., and to continue normal system operation. But by default, our simplest mechanism here, in order to avoid an uncontrolled platform failure, is to use the BISTs and other monitoring to bring the system into a fail-safe platform state. So we need to think about what's known as the diagnostic test interval. The interval between BISTs is sometimes called the diagnostic test interval, or DTI. If we are to avoid uncontrolled platform failures and we have only a single processor in the design, then the DTI must be less than the PST FTTI. For platforms that operate for only a very short period, we may not need to perform BISTs at all. This is uncommon. How do we determine the DTI? There are some indications on this slide of different DTI rates that may be appropriate for use with some of the platforms that we will discuss in this course. We'll say more about these platforms in video 21. I should make it clear that the DTI rates that are listed on this slide are intended to form the basis for a discussion when considering any particular platform. These are not the particular values that you use will depend on various aspects of the design and will vary depending on the precise design requirements. That brings us to the end of this video. Before you continue with the course, please read Chapter 16 in the ERES2 book. Thank you for watching.